can we do far better than what we are doing right now? The main reason behind it is following, that typically genome assembly involves many reads or three-mers, and we have to actually use those three-mers and create a genome assembly. In that case, what will happen is that we have to repeat often the same operations again and again, and it might leads to a longer time to generate a genome from the reads. Hence, what we are going to do is, now we are going to use a graph theory to actually improve our approach. So before I go that, what I am going to do is I am going to define two functions over a k-mers. The first function is a prefix function. In prefix function, what I am going to do is I am going to apply this prefix function on k-mer, and the output is going to be the first k-1 nucleotide of the k-mer, or first k-1 letters of k-mer. There is another function which is suffix function. Before that I'll explain the example. In this example, I have taken a prefix function and applied on ATGC, which is my k-mer, this is a 4-mer, and after applying a prefix function, the output is ATG. Similarly, when I apply prefix function here with CGTA, I will get CGT as my output. Another function, which is a suffix function, it does little opposite to prefix. It keep last k-1 nucleotide of k-mer as an output when input is provided as a k-mer. Let's take an example. For the same example, suffix of ATGC is equal to TGC, and suffix of CATG is equal to ATG. Correct? Last three in suffix and first three in a prefix. Now, there is an interesting concept which is emerging here, which can you see? If you see that k-mers are overlapped with one another, and that has an interesting aspect when we look at the prefix and suffix. So here you can note that for this particular example and this particular example of k-mers, we have prefix of ATGC is equal to suffix of CATG. Both are ATG. And this is a case in a certain cases when we are dealing with overlap k-mers. Now, question is, can we use this particular idea and extend it to develop a better algorithms and sequences to sequence or assemble the sequence. So how we can go from the k-mer to directed graph is the question we are going to address here. So as I told you, not that certain cases prefix of k-mer are equal to suffix of k-mers. So can we construct a graph or a directed graph where each node represent a k-mer and each edge between two nodes, if suffix of k-mer is equal to prefix of k-mer, then we put a edge between those two nodes. So I have a node. I'll take an example here. So what I'll do is I will construct a node AAT ATG GTT TAA and TGT. And then I will actually take all this, compute the prefix and suffix for all of these k-mers. For example, here for AAT, I will suffix and prefix, and this one is a k-mer. AAT. So there will be AT, prefix will be AA. Recall. Prefix the first k1 minus 1 nucleotide of k-mers, suffix last k minus nucleotide of k-mer. Correct? So we do that. Similarly, for ATG, suffix will be TG, prefix will be AT. GTT, suffix will be TT, prefix will be GT. Then TAA, A, T, TA and TGT, GT and TG. Now we can look at it and see there are a set of places we have a suffix of k-mer is equal to prefix of k-mer. First example is this one. Here suffix of AAT and prefix of are same. Similarly, these two are same, these are same, and these are same. So we should have an age between these two, AAT and ATG. So we'll add an age. Similarly, we have age between AAT and TTA. You can see this one. So we'll add one age. Similarly, we have an age between TGT and GTT. So we'll add another age. And in the same manner, we have TG, TG for ATG and TGT. So we'll have another one. Now, what we can do is, these are indirected edges. We can actually put a directed edge if the suffix of k-mer is equal to prefix, then suffix to, no, sorry. Yeah, suffix to prefix. So for example, TAA to ATG, we have an arrow. Now how we can do an arrow between ATG and AAT? Here the suffix of AAT is prefix of ATG. Then there should be arrow from suffix to prefix. Similarly, here ATG suffix is equal to TGT prefix. We are doing the same. And similarly for this one. Now, I have a graph and there is a direction to it, and I am going to follow this direction, okay, and I can follow this direction, correct. So what we can do is we can start from the k-mers and create a nice graph out of it. I'll rub it so that you can see the final output of the system. For the same example, we have first unlabeled or undirected graph, and therefore the same example with we got the label graph. This label graph is called overlapping graph, where we have a directed graph moving from the one k-mer to other k-mer. Now, if we look at it in the state for in this particular example, we'll realize that the solution is that we have to identify a path in this overlap graph or directed graph where we visit each of the node in a graph exactly once. If I do that and I have a path, then I can construct genome or assemble genome. So here, if I start from this node and go to the another node using this path, then I can go to this another node using this path, from this node to this path, and this node to this path. Then finally what I have is, since I have overlapping graph, I have all the elements which I know that has to be there. Here I can actually construct what I was looking for earlier in my approach. And that also allows me to, that also allows me to construct a sequence. Given this, how to compute the sequence is known. The only thing is that how to construct these overlapping steps. And here we can see that these three merges allow me to do that. Hence, what I am looking for here is a very interesting concept in the graph theory called Hamiltonian path. The path which basically is a path where we are going through each of the node in the graph exactly once. And that particular path is called Hamiltonian path. And finding such a path in a directed graph or indirected graph or undirected graph is a Hamiltonian path problem. How we can actually solve this problem? There are certain algorithms available to solve them. Let's take a more complex example and realize what are steps involved to solve the problem. So we at least look at some sanity check. We count number of k-mers, there are 16 here. And once we have a k-mers, they are overlapping, we know that what should be the length of assembled sequence. Remember that n minus k plus 1 allows you to actually compute also length, so which is here 18, so my sequence should be of length 18. What we have to do is identify the first k-mer, and we have to search for where the k-mer that does not share its prefix with the suffix of any other k-mer. So that are our first starting k-mers. If we are lucky, we have only one k-mer. In this case, the ATG is that k-mer, which is going to be a starting k-mer. We are going to use that. Once we have starting k-mer, we want to start building a graph using the prefix and the suffix functions, where suffix of particular k-mer is equal to prefix of another k-mer, then there will be a directed edge from the suffix k-mer to the prefix k-mer of that k-mer. Okay. And then we keep doing it. Here we can see that TGC is the one option available to us to solve the problem. And also remember, as I told you, that there are multiple next steps or multiple options are available, so that you have maybe have 4 or 3 roads or 4 roads or 5 possibilities, etc., to actually choose from. And you have to make a choice based on certain, which technically we do equal choices, so we randomly choose one, explore that path. If we reach to the end and use all the k-mers in my set, then we found a path which is a Hamiltonian path. Otherwise, I have to come back and then explore another path. So this is overlap graph which I have constructed by applying the algorithm we have studied. Here again, remember, each directed edge is from suffix to prefix, and you can see that there are multiple possibility. For example, when we go here CGC, I can go to GCA or go to GCC or GCG here. And what we did is we found a Hamiltonian path by looking at the all option, and we started with this one and we ended up at CCG. And since we used in CCG in such a manner that CGC was used, we cannot extend the path. But we used all of them and found a reconstructed sequence ATG, CCC, AGC, CTA, GCG, CCG. Voila. So we found a Hamiltonian path where each of this node has been visited once, and together they, when we construct the overlapping graph, overlapping sequence, and then we merge it to get a reconstructed sequence. Now, Hamiltonian path is a good approach to actually extend or improve our approach. However, we have some distinct disadvantages with Hamiltonian path. As I told you earlier, that we generate millions of reads when we try to perform genome sequencing task, and this is typically sequence experiments output. And constructing a graph for such a big system is quite difficult with such a big reads, with such a big number of nodes and edges. It's not straightforward. It's not impossible, but it's not straightforward. And think of that. For example, if we have a million reads, I have to actually look at trillion pairwise alignment or suffix equal to prefix, and then required to construct overlapping or overlap graph. Okay? So imagine the kind of computational requirement we have to actually construct this graph. Once we do that, we have to actually find a Hamiltonian path or cycles to actually find out a reconstructed sequence. And there are not efficient algorithms available to check and elucidate Hamiltonian path or cycles. The reason is because Hamiltonian path problem belongs to NP-complete problems for which we do not have efficient algorithms available to solve. And hence, we have to actually find more efficient way of extending our approach. In addition to that, we have not discussed about many repeats available in k-mer composition, which can indeed complicate the graphs. So, with the simple problem itself, we saw that we have a very complex graph. Imagine we have a million reads kind of complex graph we create. On top of that, we have to search a path where we actually travel to each node exactly once, and for that we need an algorithm which are not efficient. Hence, we cannot extend this Hamiltonian path problem related solution to assemble genome. However, there are better way to solve the genome assembly problem using the same kind of formulations on same kind of ideas in a graph theory. So, in the next lectures, we are going to discuss about those algorithms. Thank you.